I wanted to describe a couple of things, a few things that I did from the coding side, from the Python side, in making the bifurcation plots and the Poincare section plots for the damp-driven pendulum. So I'm just going to show you a couple of lines of code. This is how I made these plots. It might not be the best way to make these plots, probably not the best way to make these plots. And you may want to do it a different way, but I just wanted to show you how I handled some of the things we have to handle for making the Poincare section plots and the bifurcation plots. So this is a portion of my code for the Poincare section plots. Is the portion of the code that follows, where I define the parameters of the pendulum. I've defined the initial conditions of the pendulum. I've defined a user function to solve the differential equation. I've defined a user function that has the differential equation for the damp-driven pendulum. It's after all that, it's where I introduce an array of times, an array of theta and phi coordinates, and then I call my function for solving the differential equation at time I plus 1 from the solution at time I and the differential at time I call that sequentially to construct the angular displacement versus time, the angular velocity versus time, i.e. the solution to the differential equation versus time. So that's done in this loop here. Now, when I made the phase space plots, when I made the Poincare section plots, for phase space plots, I often wanted to ignore the transient region and just look at the steady state region. And when I made the Poincare section plots, I don't want to plot every phase space point, every theta phi coordinate. I just want to sample them at a separation of the period of the driving frequency period. So how did I do that? I introduced two new variables, and they are n section for the Poincare sections and end transient for the avoiding the transients. So for the end transients, I just define that as a number in my array of times, in my array of theta coordinates and omical coordinates, where I observe the transients to be over. And when I would make my plots, I would start from that time rather than the first time. So that would avoid seeing the transients. And then the end section, I define that so that that number corresponds to one cycle, the cycle that I want to sample the Poincare sections at. That's the cycle that has the length of the period of the driving force. So I've got those two variables set to those two values. And then when I make the plots of the phase space, and when I make the plots of the Poincare section, that's done in these two lines here. So the upper one is for the phase space, and it's going to give me a continuous red line. And the lower one is for the Poincare sections. It's going to give me the blue points. And I eliminate the transitory region, and I only take the Poincare sections by slicing the arrays inside these calls to the plotting functions. I slice the arrays using NumPy array slicing. So for example, in the upper line, I only plot the points of theta and omega after the transitory period by slicing in this manner here. And in the lower line, I only plot the Poincare section points after the transitory period, and only with this cycle corresponding to end section, corresponding to one period of the driving force with this particular slicing here. So I use slicing of the full arrays of 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 the time coordinates and the theta coordinates and the phi coordinates. I use slicing to make the phase space plots and the Poincare section plots, where I ignore transients and where I only get Poincare sections with at the appropriate cycle rate. So the other comment I wanted to make was related to the bifurcation plot. So remembering the bifurcation plot, you're plotting, so the angular displacement versus the driving force, or the angular velocity versus the driving force parameter. To do that, I introduced an additional for loop. So I had nested for loops in my code to carry out, firstly, there's a loop associated with evaluating the function, the solution to the differential equation, where I walk through the time coordinates. And then there's going to be a new loop now where I vary the value of the driving force to explore that axis of the damp-driven pendulum. And you can see this here. I've got a nested loop. So I've got one loop in which the outer loop, in which I'm going to walk over the range of driving force parameters. And then I've got the second loop, second for loop, in which I walk over the time array, finding the solutions for theta and phi. So that's a difference here. And I set up some initial parameters upstairs here for my range of alpha and my number of points of alpha that I was going to explore. So in this particular case, I started with alpha of 1.05. I'm going to explore alpha of a range of 1.05 to 1.07. That's a range that we talked about in the lecture class. And I sampled 200 different values of alpha in that range. The second thing that was useful when I made the Poincare section plots was useful when I was making was useful when I was making bifurcation plots, was useful when I was making bifurcation plots versus the angular displacement. The challenge with the angular displacement is that when the pendulum loops the loop, so maybe it loops the loop clockwise or it loops the loop anti-clockwise, counterclockwise, then the angle coordinate, the angular displacement picks up factors of plus 2 pi or minus 2 pi. To make the bifurcation plots, I redefine my theta. I redefine my theta to be in the range minus pi to plus pi. And I redefine theta by basically taking the theta coordinate, dividing by 2 pi, and taking the remainder. And that's that remainder I use to redefine theta in the range of minus pi to plus pi. I don't want to care about, for the bifurcation plots, that the pendulum has looped the loop. Especially I don't want to care if it keeps looping the loop in, say, the positive direction. And so it spreads out the bifurcation plot, or it loops the loop in the negative direction. It just stretches out the bifurcation plot. I just want to know theta's in the range between the far right and the far left-hand swing of the pendulum. And so I did that with this little line here, where I divide by 2 pi, I find the remainder, and then I put that remainder from 0 to 2 pi, I put it on the range of minus pi to pi. And it's that I work with when I make the bifurcation plot.